one from Math 2000. It's linear algebra. Professor Wenson here with a video on your ZyBooks Section 5.2 titled Spanning Sets. So this section is going to have a few new definitions for you, and of course I'll work out some examples when we get there. Alright, so again, you can read the section summary. Got the objectives here. Alright, so the first part of this section is on something called a linear combination. You may have heard that. I think we've brought this term up before, but here it is again. So given a finite set of vectors, a new vector can be obtained by performing scalar multiplication or vector addition, or both, on the given vectors. So suppose v1, v2, all the way up to vn are vectors in Rm. Right? So that means each one of these vectors has m components. And suppose a1, a2, all the way up to an are scalars, right, are real numbers. The linear combination of the vectors and the scalars is just the sum of their products. It's the sum from I equals 1 to n of ai times vi. So a1 times v1 plus a2 times v2 plus all the way up to an times vn. Alright, it's the sum. The linear combination of the vectors and scalars is just the product of those scalars and their corresponding vector added up. Right. The scalars, right, a1 through an, in this linear combination are called the weights of that linear combination. Right. Now, since Rm is a vector space, scalar multiplication and vector addition result in another vector in Rm. Remember how scalar multiplication and vector addition. Remember how in a vector space those operations were closed. Right? You had closure. So if you take two linear combinations, add them together, you're getting another linear combination of vectors from Rm. You take any vectors from Rm, multiply them by a scalar, you get another vector from Rm. Alright, the animation below provides a geometric interpretation. Let's take a look. So remember, the sum of two vectors is a linear combination. So there's v1, v2. This is a linear combination with weights 1 and 1, right? The scalars here are 1 and 1. Those would be the weights of that linear combination. Other linear combinations can be obtained by scaling each vector and adding the results. So here's a1 times v1, a2 times v2. There's a1 v1 plus a2 v2. Here's a3 times v1, and they add a3 v1 plus a2 v2, whatever. You just add scalar multiples of a couple vectors, of a bunch of vectors, and you get what's called a linear combination of those vectors. Alright, so their example here. So suppose we're given v1 is the vector 5, 1. So this is a vector from R2, right, two-dimensional space. And v2 is the vector with components 3 and 4. So the first question is, I'll do this on some paper. What vector is formed by the linear combination a1 v1 plus a2 v2, right? So again, the sum of scalar multiples of these vectors, given that a1 is negative 3 and a2 is 7. Right. So I have here written out those two vectors from the example and the two scalars. And a1 times v1, that's negative 3 times the vector 5, 1, plus a2 times v2, that's 7 of the vector 3, 4. And hopefully you recall how to do simple, the way that we defined scalar multiplication and vector addition in Euclidean vector spaces last, a section ago. When you multiply by a scalar, you multiply each component by that scalar. So negative 15, negative 3 there. And same with this, 7 times this vector would be 21, have components of 21 and 28. And then vector addition, you simply add the corresponding components. So negative 15 plus 21, positive 6 for the first component, and negative 3 plus 28, positive 25. And then here's the resulting vector. So what we would say here, we would say that the vector 625 is a linear combination of V1 and V2 is how we would say this. All this means is that I can get this vector by multiplying the first vector by a scalar, multiplying the second vector by some scalar, and adding them up, which we have done here with the weights negative 3 and positive 7 to get this vector. All right. Okay, so back here, now they see they got the 625. All right. Part B, which weights should be used to obtain vector B here? So what should I multiply V1 by? What should I multiply V2 by to add them up, get a linear combination that makes the vector 2, negative 3? So again, I'll go to a piece of paper with this. All right. So again, the same vectors, but now the question is, can we find those weights? Can we find the scalars A1 and A2 such that, A1 V1 plus A2 V2, this linear combination of these vectors makes the vector 2, negative 3. So look at what happens here when we're trying to answer this question. Another way to ask this would be to ask, is this vector 2, negative 3 a linear combination, right? So I could also ask it this way: is the vector 2, negative 3 a linear combination of the vectors v1 and v2? That's another way to ask this same question. All right, so let's see what happens when we ask that question. Is one vector, a linear combination of another set of vectors? So what does a1 v1 look like? Well, that would be 5 times a1, and then 1 times a1. And then what does a2 v2 look like? Well, that'd be 3 times a2 and 4 times a2. And in order for these to be equal, this sum to be equal to the vector 2, negative 3, we'd basically be solving the following system of equations. We'd have 5, I would need 5a1 plus 3a2 to be equal to 2, the first component. And I would need a1 plus 4a2 to be equal to negative 3, right, the second component. And we've already seen how to solve systems, and really that's what it's going to boil down to. A lot of stuff we do in this course is going to boil down to solving a system of equations. All right? And we know how to do this. Now you could do this through elimination, through substitution. All right, I'm just going to do it the way we've been taught to do it. Make a little augmented matrix. 5, 1, 3, 4. The coefficients of a1, the coefficients of a2, and then the constants over here. Now, there's only a couple rows. I'm going to tell you right now, in a lot of this, I'm just going to be going to the calculator from now on. We already did all the chapters on Gaussian elimination and Gauss-Jordan elimination and elementary row operations. So I'm assuming you know how to do that stuff. So what I'm going to do in a lot of videos from here on out is say, hey, here's my matrix setup. Let's put this into reduced row echelon form with our calculator. All right, so I'm going to pull a calculator up. enter this matrix, and I'll be right back once the matrix is in reduced row echelon form. And so I entered this 2 by 3 matrix, and just had the calculator do it for me. Again, I'm assuming you know how to do it by hand. We've already done those chapters where you did it by hand. We're going to be kind of past that now. Alright, that's not the important part anymore. The important part is now the final result. And we got 1, 0, 1 for the first row, 0, 1, negative 1 for the second row. So I'm seeing from this system here that the value of A1 is 1, and the value of A2 must be negative 1. Right. So yeah, the answer is yes. The answer to this question, this system had a solution. So the answer to this question, is the vector 2, negative 3 a linear combination of 5, 1, and 3, 4? The answer is yes, and here's how. I take 1 times 5, 1 plus negative 1 times 3, 4, and that will give me the vector 2, negative 3. And then we'll check this, 5 plus negative 3 is 2. 1 plus negative 4 is negative 3. This does indeed work out. But we're going to see that all this linear combination stuff, determining if one vector is a linear combination of a set of vectors, a bunch of other vectors, it's going to boil down to the solution of some system, whether or not a system of equations has a solution or not. All right? And again, now they just said by inspection, it's like, I can see if I take one of this and minus, if I just subtract these, I'll get 2, negative 3. I mean, it's not always going to be that easy, though. Right? Like I said, we're going to, I'll be setting up systems every time. All right. All right. Now this, I'll just leave this to you. Is the vector negative 24, negative 1 here a linear? Is it this linear combination of negative 10, 3, and 4, 7? Just, negative 20 plus negative 4, yeah, that's negative 24. 6 plus negative 7 is negative 1, yes, this is true, and then I'll leave the second one to you. All right, easy enough. The challenge activity is, again, pretty simple. This first level is just, here's vector v1, here's vector, v2, and they give you the weights. They give you the values of these scalars, 4 and 2. And they say, what vector is formed by the linear combination of those two vectors, a1, v1 plus a2, v2? So if I take 4 of this and 2 of that and add them together. So the first component would be negative 16 plus 18. That'd be positive 2 for this new vector, this linear combination. The second component would be negative 36 plus negative 14. That'd be negative 50 for the second component of the linear combination. I check and looks great, and I move on to the next level, and there are 4 of these. I think they're all similar. Let's see. Yeah, this is just with vectors from R3, right? Just with vectors with 3 components. They give you the weights, they give you the values of all these scalars, and ask you for a linear combination of those 3 vectors. And let's see what the last level looks like. Alright, so this is the other way around. This is saying, hey, is the vector 122 a linear combination of these 2 vectors here? And if so, what are the weights? What could the weights be? Alright, so this one I'll actually set up a little system. Well, I'll leave this to you actually again. You set up a system where you're going to be solving for A1 and A2. Where down one column you'll have this vector, another column you'll have this vector, and then you have a little bar, a little line, and then this 122 on the other side, and put it in reduced row echelon form, or row echelon form and do back substitution, and find your weights that way. Okay. So now, next part. expressing a system of linear equations as a linear combination. And I showed you one way where you had a linear combination of vectors and I expressed it as a system. This is just, the other way around. So I'll just get into an example here. So they got theorems and whatnot, but so here, this is just like earlier. Finding the weights of a linear combination. So suppose B is, I'll get the solution out of there. Suppose vector B is the vector 4, 7. Vector A1 is the vector 2, 5. Vector A2 is the vector 1, 4. Find vector X, basically find the weights. Find x1 and x2, these numbers, such that x1 times a1 plus x2 times a2 equals b. So I want to show that b is a linear combination of the vectors a1 and a2. So again, I'll write this out. And so again, here's the vector a1, a2 from that example. They're asking me to find another vector of constants here, a vector of, what are the value of x1 and x2 such that x1a1 plus x2a2 equals the vector 4, 7. Right. So if I substitute this stuff, right, remember what this, like I said, you're going to get a system here. X1 times a1, again, x1 is a number, x2 is a number, these are scalars, weights. If I multiply a1 by x, that'll be 2x1 and then 5x1 plus, and then if I do the same to a2, x2 times vector a2, x2 times 1, 4 here, I'll have x2 and then 4x2. And I want this to be equal to the vector 4, 7. Again, this leads me to a system where, the first components need to be equal, right? So 2x1 plus x2 needs to be equal to 4. And the second components all together need to be the same. 5x1 plus 4x2 needs to be equal to 7. And remember how we can express a system of equations in many different ways. As a matrix equation, I could express this as the coefficient matrix, where down the first column are the coefficients of x1, and that's just the vector a1 in the first column there, 2, 5. And then the second column is the coefficients of x2, 1, 4. And that's just the vector a2. Right, that's just that vector a2 here. And there's the coefficient matrix multiplied by the variable matrix with x1 and x2 in it. And this is that vector x that was being mentioned up here, the variable vector. And I would like this to be equal to the constant vector 4, 7. Sorry about the tightness of this. And this is that vector b that's being mentioned. So you could write it like that, or as an augmented matrix, where again, down the first column I'm going to have vector a1. Down the second column I'm going to have vector a2, have a little bar, and then that vector b on the other side. So I'll write that out with the numbers in it. So 2, 5 down the first column, 1, 4 down the second column, 4, 7 down this third column after the bar. And then, like I said earlier, I know like I said, there's only 2 rows here. It wouldn't take that long to put this into reduced echelon form. But I'm just going to have the calculator do it for me, because that's not the important part anymore. Alright, it's not like earlier chapters. So I'll be right back with bring the calculator up here. I'll be right back with that calculation. Okay, so I entered the 2 by 3, put it in reduced row echelon form, and it resulted in this matrix. And we have our solution. Then we have our weights. From this we're seeing that x1 needs to be 3, and x2 needs to be -2. And let's check that. All right, let's check and see, you know, are these the good weights for a linear combination of a1 and a2 that'll make the vector 4, 7. So is 3 times a1 plus negative 2 times a2, you know, is that equal to the vector 4, 7? Let's see. First components, you know, 3 times 2 plus negative 2 times 1, that'd be 6 minus 2, that'd be 4. That's good. Second components, 3 times 5 would be 15. Negative 2 times 4 would be negative 8. 15 plus negative 8 is 7. It works, right? And again, something else I would say here is that the vector 4, 7 is a linear combination of a1 and a2. Right? That means I can find weights like we did here, such that, you know, the product of those weights with the vectors and then the sum of those products make the vector 4, 7. All right. So 3, negative 2. All right. So you're asked to do the same thing here. So again, it says consider the vector b, and then vectors a1 through, you know, an. And you're supposed to find weights x1 through xn such that b can be written as a linear combination of those vectors a1 through an. Alright, so I already did. Now notice they're only asking for one particular component. You know, here they gave you x1, they want x2. Here they gave me x2 and x3, they want x1. Alright, so I'll do this second one on some paper. So again, with this, we have this vector b, you know, 16, negative 8, 0. a1 is 7, 3, 5. a2 is 5, negative 5, 3. And a3 is negative 3, 2, negative 7. We're trying to find these weights, right, these values of x1, x2, and x3, such that, you know, x1, a1 plus x2, a2 plus x3, a3, this linear combination of a1, a2, and a3 is equal to vector b. So remember, I'm not going to do all the writing that I did in the previous examples. And this leads me to a system that I can then express as an augmented matrix. We're down the first column, we'll go the coefficients of x1, which will be just vector a1. 7, 3, 5. And then down the second column, we'll go the coefficients of x2, which will just be the components from the vector a2. Right, 5, negative 5, and 3. Down the third column will basically, you know, be the coefficients of x3, which will be the components of vector a3. So negative 3, 2, and negative 7. Then a bar. And then vector b, you know, what we want it to be equal to, what we want this linear combination to be equal to on the other side. These are 16, negative 8, and 0. And hopefully this system has a solution. If it doesn't, that means that this vector cannot be written as a linear combination of those three. But let's see. Alright, so now I'm going to go to the calculator, put this into reduced row echelon form, and again, so I'm just going to enter this 3x4 matrix on my calculator and come back when it's in reduced row echelon form. Alright, so I'm back here. You see on my calculator screen, reduced row echelon form. Looks like this does have a solution. Right? Sometimes it won't. There are going to be some times, and we'll come across it in a minute, where, you know, one vector cannot be written as a linear combination of other vectors. You know, the system doesn't have a solution, but this one does. It looks like the value of x1 I need is 1. The value of x2 that I need is 3. And we have 1x3 equals 2, right? So the value of x3 is 2. And we can check this. You know, is 1 times vector a1 plus 3 times vector a2 plus 2 times vector a3, you know, is that equal to the vector 16, negative 8, 0? Is that equal to vector b here? So I go back, and we can do a quick little mental check here. So looking at the first components, 1 times 7 is 7, 3 times 5 is 15. Add those up, you make 22. Then minus 6 would be 16. So the first component works, and I'll leave the other two to you. This works. So then back in the website, see they already gave me x2 and x3 were 3 and 2. The only one I'm filling in is x1 here, which was 1. All right, the first weight. All right, so now on to the concept of span. All right, so the span of a set S. All right, so say a set S contains n vectors, vectors v1 through vn. The span of this set of vectors, which is denoted span of S, is the set of all linear combinations of those vectors. So the way they write it here is the span of the set of vectors v1 through vn is, again, the set of all linear combinations of those vectors. Right? And remember what a linear combination looks like. It's the sum of scalar multiples of those vectors. That's what they're expressing here. Right. So if a set V is equal to the span of some set S, then they say that S is the spanning set of V. Or they say that V is spanned by S. So when you say this, a set V equals the span of set S, all that means is that every vector in V can be written as a linear combination of a vector in set S. Because that's what the span of S is. The span of S is all possible linear combinations of the vectors in set S. Okay. A subset of a vector space generally does not form a subspace. Remember this word from section 5.1. For example, this set here, W, with just these two vectors, the vector -2, 4, and -8, 11. The set with just these two vectors in it is not a subspace of R2. Remember, it wouldn't satisfy all 10 of those vector space properties. It's definitely not closed under addition, right? If I add these together, I'd get -6 and 7. Well, the vector -6, 7 is not in here. So it's not closed under addition. It's definitely not closed under scalar multiplication, right? This does not satisfy, this set of just these two vectors does not satisfy all 10 vector space properties. So it wouldn't be a subspace of R2. Because again, W does not contain the 0 vector. That was another. Remember, to be a subspace of a larger vector space, you had to contain at least one vector, right? Usually we looked for the 0 vector. You had to be closed under addition and closed under scalar multiplication, right? Remember that again, hopefully you remember that from section 5.1. However, the span of any subset of Rn always forms a subspace. Because remember, the span of a set is all linear combinations of that set. And that's closed under addition, right? You take a linear combination of vectors, add it to another linear combination of those same vectors, you're going to get another linear combination. It's closed under vector addition. If you take a linear combination of vectors, multiply it by a scalar, you're going to get another linear combination of those same vectors. So it's closed under scalar multiplication as well. So that's what they're saying here. For a subset S of Rn, if you look at the span of S, right? If W is the span of S, the set of all linear combinations of the vectors in S, that span of S is a subspace of the Euclidean space Rn. All right, they take you through here. Now, they show you a picture here. Now, if I'm in R3, all right, if I'm in R3, the span of a single vector, if you just have a single vector, the span of V, that's going to be forming in R3. It's going to form a straight line containing the origin. Because all the vectors that are linear combinations of one vector are just the scalar multiples. All right, if you have a single vector and you're asking for linear combinations of a single vector, that's just scalar multiples of that vector. So you're going to get all these vectors that form a line that run in the same direction or the opposite direction as v. Now, if you have two vectors that aren't on the same line, like here in this picture, v1, v2, pointing in different directions, the span of two vectors that are not collinear form a plane, right? All the linear combinations of two vectors form a plane containing the zero vector containing the origin. Now, this is just a couple of examples. We'll take a look at spans of 3 vectors, 4 vectors, whatever. All right. Let's see. If a vector B is in the span of S, then there are scalars such that B is a linear combination of those vectors. All right, so this is what I've been saying all along, right, about linear combinations. Suppose A is the matrix formed with the vectors in this set. So that means column 1 is vector 1, column 2 is vector 2, column 3 is vector 3, and so on. A vector B is in the span of S if and only if A times X equals B has a solution, and we've been seeing this. This is saying that a vector is a linear combination of other vectors only when there's a solution to that system. And we'll go in examples here in a second. All right, so S spans the entire space Rm, or equivalently the span of S is equal to all of Rm if the corresponding system of linear equations has a solution for all vectors B in Rm. All right, so the following theorem is useful in determining whether S spans the entire space Rm. All right, so if you want to determine whether a set of vectors spans the entire space Rm, right, if every vector in Rm can be written as a linear combination of the vectors in set S, then you can do the following. So suppose A is an m by n matrix formed with vectors in set S, right, vectors v1 through vn as columns. The following statements are equivalent, meaning that if one of them is true, they're all true, and if one of them is false, they're all false. Right. So if the span of S is equal to the entire space Rm, means the same thing as the system Ax equals B has a solution for every single vector in Rm, right? Every single vector in Rm is a linear combination of the vectors in S. That's exactly what it means for Rm to be the span of S. And when does this system have a solution? For any vector B? When A has an inverse. Well, not an inverse, but when the reduced echelon form of A has no 0 rows, because this isn't always a square matrix. I shouldn't have said inverse, right? Only square matrices have inverses. But when does a system like this have solutions? For every vector B, not just for a single vector. If you were to put it in reduced row echelon form, if there's no rows of completely zeros in the coefficient matrix, then the system will have a solution for every B. All right, so let's keep this in mind. All right, so for instance, and I'll do a few of these, right? So here, say v1 is this vector from R, these are from R3, right? The three component vectors. Say v1 is this vector, v2 is this vector, v3 is this vector. Is the vector 3, 2, negative 3 in the span of these three vectors? So basically, that's the same question. Is this vector a linear combination of these three? Because remember what in the definition earlier, the span of a set of vectors is the set of all linear combinations of those vectors. All right, so I'm going to write this out. So here's the three vectors mentioned. And the question is, is the vector B equal to, 3, 2, negative 3? Is this vector in the span of the set with the three vectors that we're seeing up here? All right, now remember what the span of a set of vectors is again. The span of a set of vectors is the set with all possible linear combinations of those vectors. So another way to ask this question, an equivalent question, is vector B here a linear combination of these three vectors? That is the same question, because if the answer is yes, then this vector is in that set. It's in the span of that set. And if the answer is no, then this vector is not going to be in the span. Right? In order to be in the span of a set of vectors, you must be a linear combination of those vectors. Right, and then this all is equivalent to basically solving this system. Now you'd end up setting up a system with an augmented matrix where, down the first column is vector v1, down the second column is vector v2, down the third column is vector v3, and a bar here, and then down the third, and then the other side of the equal sign is the vector you want to see if these three vectors, if there's a linear combination of these three vectors that make this vector 3, 2, negative 3. All right, so again, I'm going to go to the calculator and have it put this into reduced row echelon form for me, and I'll be right back with that. Alright, so I put it in reduced row echelon form, and had it changed to fraction. I hit math, change to fractions. Here's what we end up with. 1, 0, 0 down the first column, 0, 1, 0 down the second column. You have 5 thirds and 11 thirds and 0, and then bar, and then 0, 0, 1. Look at that last row. This would be 0x1 plus 0x2 plus 0x3. 0 equals 1. A false statement. And in fact, you don't need to even look at the right side there. You can just look to the left of the bar. When I take my coefficient matrix, the coefficient matrix in reduced row echelon form here has a row of zeros. And that means that there are some vectors out there that won't be in the span, like this one, right? We can see. Now, I could have chosen some other vector that might have worked. That might have given you 0 down here, and 0 equals 0 is fine. But in order to be, in order for every vector to be in the span, this has to work all the time, and this is not going to work all the time if there's a row of zeros in our coefficient matrix when it's in reduced row echelon form. So based on this, no. The answer is no. I cannot find. Right? There are no scalars. There is no x1, x2, x3 such that x1 v1 plus x2 v2 plus x3 v3 is equal to b. This cannot happen. And again, you don't even need to do the right side here. If you put your coefficient matrix into reduced row echelon form, there's a row of zeros. I mean, again, it might work for one vector, but it's not going to work for all vectors. Right? So back here, the answer is no. Again, that went through here. All right. Now, all I need to do in these next couple is just change that right side. So back here, so for part 2, the question was, okay, same 3 vectors, right? Same 3 vectors. But now the question is b equal to, what is it, 1, 0, 0 in the span of those 3 vectors? Is it a linear combination of these 3? Now the last one wasn't, but this one might be. All right, so I still have to check. Now the only change that I would make is the system, again, the first column vector v1, second column vector v2, third column vector v3, and then bar, and then 1, 0, 0 over here. So the only thing when I go to the matrix in my calculator, second matrix, the only thing I need to change in my 3 by 4 there is the far right column. All right, the first 3 columns are the same. I'm just changing this last one to 1, 0, 0. Get out of here, go matrix, math, to reduced row echelon form, and then matrix A, it was called matrix A again. All right. And I'll change the fractions, math, change the fractions, and now this one's okay. Right, the last one had a row, yeah, sure. Now look, the left side's going to be the same all the time, right? See how the left side earlier in my first example, 1, 0, 5 thirds, 0, 1, 11 thirds, and 0, 0, 0. That's not changing. This reduced row echelon form for the coefficient matrix, that won't change. Just this other side, that'll determine whether or not the vector belongs to the span. That'll determine whether or not that vector is a linear combination of the vectors. So in reduced row echelon form here, we got 1, 0, 0, 0, 1, 0, 5 thirds, 11 thirds, 0, and 1 third, 0. Now I know there's a row of zeros here, but if you look at the whole thing, that's 0 equals 0, and that is a true statement. That's fine. And there's a free variable here, right? x3 is free, right? The third column has no pivot, right? The first column has a pivot, the second column has a pivot, the third column doesn't have a pivot. So remember, so that means, not only can I write 1, 0, 0 as a linear combination of these 3 vectors, I can write it in infinitely many ways. This system with the vector 1, 0, 0 on this side has, infinitely many solutions, whereas when it was 3, 2, negative 3, it had no solution. Right. So let's test that out. So remember, x3 is free. From this first one, you got x1 would be equal to 1 third minus 5 thirds times x3. And then from the second row, you'd have x2 would be equal to 1 third minus 11 thirds times x3. So so I could replace x3 with anything. So like, let's say let x3 be, let's do something good here. How about 2? Just to I want to plug in something for x3 that'll make these nice integers. If x3 were 2, then x1 would be 1 third minus 10 thirds. So it'd be negative 9 thirds or negative 3. And x2 would be 1 third minus 22 thirds. Right? 11 thirds times 2. That's negative 21 thirds. That's negative 7. And let's see. Let's check these out. These weights, negative 3, negative 7, and 2. So if I take negative 3 times, v1 plus negative 7 times v2 plus 2 times v3, that should give me the vector 1, 0, 0. And let's see. Let's go back to those vectors. All right, here was v1, v2, and v3. And let's see, negative 3, let's just do the first components. So negative 3 times 5 is negative 15. Negative 7 times negative 2 is positive 14. That makes negative 1 when I add those. And then plus 2 times 1 would be positive 1, yes. And then for the second components, you'd have negative 12 plus 28 minus 16. Yeah, the negative 12 plus 28 is 16. Minus 16 would be 0. And then the third components, you'd have 3 minus 7 is negative 4 plus 4 is 0. That works. So yes, 1, 0, 0 can be written as a linear combination of these 3 vectors. And again, that's not the only way. That's not the only way. I got these weights when I let x3 be 2. But I can let x3 be anything I want and get 3 different weights and write 1, 0, 0 as a different linear combination. But 1, 0, 0, the vector 1, 0, 0 is in the span, does belong to the span of those 3 vectors. It is a linear combination of v1, v2, and v3. All right, so I have one vector that wasn't in the span. Here's one vector that is in the span. Again, they talk about system has infinitely many solutions, as I said. Is 0, 0, 0 in the span? Absolutely. Absolutely. Because if you put 0, 0, 0 on this right side, the last row would be full of zeros. I promise you. Because again, this left side, the coefficient matrix in reduced echelon form, that's not going to change. See, that's the same up here. It's the same here. So yes, it will be. Now, is the span of these 3 vectors going to give me every vector in R3? Well, no. I mean, we just saw that here's a vector from R3, 3, 2, negative 3. That's not in the span. So no, this is not true. Right? If this were true, that means that every vector in R3 would be a linear combination of these 3 vectors. But we saw there is a vector that's not. And again, from the theorem up here, a really easy way to check that is if you take the coefficient matrix and put it in reduced echelon form, and it's got a full row of zeros, right? You see the 3 zeros there, the 3 zeros there. If it's got a row of zeros, that means there's some vectors that'll work and some vectors that won't. All right, we saw this one not working, this one does work, but it won't work all the time. And in order for a space to be equal to the span of a set of vectors, it has to work all the time. So no here because of that row of zeros. And they show that here. All right. Now, if this didn't have a row of zeros, then it would always work, and this would be true. So you gotta be careful. You gotta pay attention. All right. Then the last challenge activity is again you're given. It says which of the following describes the span of set S. So let's start it here. Now, this has 3 vectors. All right, 3 vectors. Now, would they all be on the same line? Now, the origin is just the 0 vector. Oh, you can't see that, can you? Oh no, I'm looking at the recording here. You cannot see what I am seeing. When you hit the select button, there's 4 options. One says just the origin, which is just a 0 vector. A line through the origin. R3, is it all of R3? And a plane through the origin. All right, so let me show you how to determine what kind of a space this is going to be. This is kind of related back. This is related to this picture up here. They talk about geometrically what the span of a set of vectors. The span of a single vector is a line through the origin. The span of 2 non-collinear vectors, 2 vectors that point in different directions, is going to form a plane through the origin. The span of 3 vectors that aren't on the same plane, right? So 3 vectors that point in 3 different directions, that aren't on the same plane, will form all of R3. All right. So it's related to that thing there. Now let me show you how to easily determine what the span of this set will look like. So I'm going to go to a piece of paper here. Okay, so we're asked about, what does the span of this set S look like, or describe it. Remember, the span of this set is all linear combinations of the vectors in this set. So it's all it's going to be all the values that look like this. X1 times 2, 4, 1, or 2, 4, negative 1, plus X2 times negative 2, 2, negative 2, plus X3 times 4, 0, 3, where x1, x2, and x3 are real numbers, right? They're scalars. There's a description of the span. Now, when they talk about describe it geometrically, right? These are all vectors in three-dimensional space. Real easy way to determine what kind of a picture you're going to form with the span is take a look at the, if I was setting up, remember how if I wanted to find out what vectors are in the span and what vectors aren't in the span, I set up a system and the coefficient matrix had these vectors, right? Down the first column is 2, 4, -1. Down the second column is -2, 2, -2. Down the third column is 4, 0, 3, and then I had some equal sign, then some vector b over here that I don't know, right? I'm picking any vector from, b is some vector from R3. And then we put this in reduced row echelon form. So all I'm going to do here is put the coefficient matrix into reduced row echelon form. And I'll have the calculator do that real quick. Okay, so I entered the 3 by 3 coefficient matrix and put it into reduced row echelon form, and it looks like just the identity matrix. And again, I don't know what's on the other side of this, because again, I'm doing this for any vector, but you can see how 3 pivots, no rows or zeros, so every vector in R3, this tells me that no matter what b is, no matter what I plug in for b, this will have a solution. There will be some value of x1, x2, and x3 such that a linear combination makes vector b, whatever vector b is. So this tells me that the span of this set of 3 vectors is all of R3. Right? It's all of R3. Every single vector in R3 can be written as a linear combination of these 3 vectors. All right, so back here now, again, I know you're not able to see when I hit the select bar, some stuff comes down. One of the options is all of R3, and you're seeing R3 pop up there. All right, then I check. Great. All right. Now, again, that was because all 3 columns were pivot columns here. If only 2 of them were, then I'd have a plane instead of all of R3. And if only one of them was a pivot column, then I'd have a line, right, through the origin instead of all of R3. So again, it kind of ties back to that picture from earlier. Let me take a look at the next level. All right, now this time, it says which of the following vectors is in set S, is in the span of these 3. So which of these 3 vectors, and there could be more than one, you gotta select which ones, which of these 3 vectors is a linear combination of these 3? So you're going to set up a coefficient matrix. You're going to set up an augmented matrix with this column first, this column second, this column third, and then you just make this column the 4th one, put it in reduced row echelon form, see if there's a solution. Then make this column the 4th one, put it in reduced row echelon form, see if there's a solution. Then make this one column 4, put it in reduced row echelon form, see if there's a solution or not. It's really that simple. It'll take a while, but with the calculator it should be easy. And let me look at the last level. Yeah, so again, determine whether this vector is in the span of these 2 vectors, right? So is this vector a linear combination of just these 2? Still, you set up a matrix with this is the first column, this is the second column, and a little bar, and then this is the 3rd column, put it in reduced row echelon form, and see, hey, is there a solution or not? So shouldn't be too bad. All right, then you have your additional exercises. Again, some of these are in assignment 8, some are not. I would still recommend doing all of them just to get more exposure, more practice, get better at the stuff. And you can also view the solutions if you wish, but please try to work them out, try to figure out what you're doing, work on the problems, before you look at the solutions. And hopefully this video helps guide you through this section with a bunch of examples. And I know I have other videos posted to Canvas too that hopefully all this stuff is helping you out. If you have any questions, let me know. And thank you very much for watching.